The seminar we're going to have here is really to present some unfamiliar characteristic of ceramic capacitor. Now, I'm sure that most of you are familiar with capacitors, so I'm not going to go into very basic details, but to point out that something which is above and beyond what we see every day as we are doing our engineering work, and also to show you some of the applications that we have come up with for taking advantage of the voltage dependence of ceramic capacitors. So this will be at the end. If you're interested, there is a Wikipedia, very nice page on ceramic capacitors. You can find a lot of information. Again, I'm not going all the very basic, although I have to start with some basic information so we'll have a common language here and we'll know what we are talking about, and then we'll proceed to the more detailed discussion. So let me go over very quickly on what we're going to do. We're going to look at the general description of commercial ceramic capacitors, data sheet, and then I'm going into some other issues. One of them start with is representing the losses by a parallel resistor, what it means, and there's a very interesting theoretical aspect to it. Something which is less known, ESR is a function of bias voltage. This is not very well known, and I'd like to show you, and there is a mystery there, and maybe some of you can solve this mystery, I don't know. Piezoelectricity of ceramic capacitor, also not very well known. And then the question of how do we model nonlinear capacitors, how we simulate nonlinear capacitors, and then the end, I'm going to show you some example of how we can use the ability of capacitance control of ceramic capacitors to build resonant, especially resonant converters with unique characteristics in which the control is by varying the capacitance and not the frequency. So this will be the end of the presentation. So one more thing I didn't say, since we are a small group, if there are any questions, please don't hesitate. You can ask. They're very happy to discuss. I may not know the answer, but I'll try. And if there are any questions, really don't hesitate, because I'm going to go over some of the subject rather quickly because we have a lot of material here and I'd like to finish it up. So I may skip on some things, and if there is a question, please don't hesitate to ask. So we're all familiar with ceramic capacitors. They are very famous and very, very useful, and also due to the fairly low price, they are used a lot, in just any design. We know the through-hole, the SMD, and of course the multi-layer ceramic capacitor, in which we have a comb type of arrangement in order to increase the surface area and also to reduce the inductance, as a matter of fact. So these are the capacitor I'm talking about. Now, the SMT types have now a standard, a size. There is different standards here. This is the size, like 0.1, 0.05. It'll be in hundredths of an inch, the length and the width of the capacitor, and then they're in inch and millimeter, different standard. And just to mention that some of these are better in terms of high frequency because they have lower inductance. You like them to be wide, not very long. This helps to reduce the inductance. So the first thing I'm going to address is polarization. Now, dielectric material can be polarized or have a polarization nature. This is very similar to the magnetization of a ferromagnetic devices or materials that we are perhaps more familiar. And we are talking about polarization, which is primarily the moment of the electrical moment of the domain that you have inside the material as it rotates when you are exposing it to an electric field. So polarization is the amount of this moment. So it's a charge, this is charge density times the displacement, you might say, of this charge as you polarize the material. This is the meaning of polarization. And then, I'm not going into fine detail, polarization then can be shown to be a function of the electric field, obviously, that this is what is rotating the domain, and psi, which is related to what we are more familiar, the dielectric constant. It's not exactly, there is a function between them. So this is polarization. So we distinguish between, say, three types of dielectric materials. We have a simple dielectric material, air, okay? Straight line between the polarization and the electric field. We have the paraelectric materials, in which we have a straight relationship, although it might be broken at a given point. And these are the paraelectric materials. And then we have the ferroelectric, which are the most interesting, and we are going to talk about it a lot. And they are very familiar to the ferromagnetic materials. They have a hysteresis, which of course is related to losses. The hysteresis relates to loss. And here there is a pictorial sort of an explanation that in this region all the domains are sort of randomly arranged. And as you impose the electric field by the voltage, they are organized along the field. Here it's for positive, here for negative. And once you get them all organized, there is no more polarization that can take place. That is, you cannot add more charge to it. And this is why we get this saturation behavior. So this is the sort of very intuitive explanation of the ferroelectric material. Now, we like ferroelectric material because they have a large relative dielectric constant, about 7,000 up to 7,000 more than air. This means that we can make small capacitors. This is the beauty of ceramic capacitors. Because this dielectric constant is large, and because capacitance is a function of the dielectric constant, of course the area and the distance, you can make very, very small. Well, there are some capacitors today that I can't see them. I mean, they are so small, amazing. Now, here is a typical hysteresis of a ferroelectric material. Here already, instead of polarization, which is related to charge, it is already in units of charge. For a given element, you can replace the two. It's a constant between them. Here is the voltage, which is again replacing the electric field. Again, for a given structure, there is a constant between them. And as we can see, there is a hysteresis, some hysteresis, and sort of saturation. Now the slope here, this is dq dV, is by definition capacitance. So here, this is a local capacitance. We'll talk about it a lot. A local capacitance at this point. And obviously, the slope here is different from the slope here. So the local capacitor here is much smaller than the local capacitor here. And this is why, if you look at data sheets, you'll find this graph, which shows you how this is now the derivative or local or differential capacitance is changing with voltage. Here is this point. Here it will be this point. Okay? So the slope here is large, and here it's going down. This is typical of ferroelectric material because they have the saturation effect. And shown here are two materials. There are many. I'll talk about some of them. I'll show some of them. And X7R is probably the most popular one. We're using them a lot because of temperature characteristics. It's not changing that much. I'll show it in a minute. And then there's another material, X5R, which is more changing. And the change is very dramatic. Not many engineers are really aware that the capacitance will change a lot. And obviously, most of the capacitor we are using in filters and converters are exposed to DC. And here you see that it goes down by 80%. That is 1 microfarad capacitor ends up to be 0.2 microfarad. And this is within the range of operation. I mean, it's not as if we're going out of the range. This is the permissible range for this capacitor. So the change is really very dramatic, and one has to be aware of that.
Excuse me. Does this change evaluate with frequency also? Or does this curve stay rather constant with frequency? Or does it change a lot?
I have some experimental results I'll show you. There is a change, but this is not dramatic. This effect is not dramatic. That's a good question.
Less losses in the saturation?
Pardon?
There seems to be less losses in the saturation region?
That's another very good question, and there is a partial answer to it, and I'm going to discuss it. Okay, so let's move on. So we have now 2 groups of material that are used for ceramic capacitor. They are the paramagnetic electric material and the ferroelectric material. And the industry designate them as class 1, class 2, and class 3. Okay? Class 1 are the paraelectric material. It's known as the COG or NPO. This is the best ceramic capacitor available. They are paraelectric, so they don't suffer from all the problem of ferroelectric. And also temperature-wise, we'll see in a minute. While in the case of the ferroelectric, we have all the problems I've mentioned. And the main difference, and the one of the difference, is also the ESR, the resistance, the losses, we'll talk about it, are lower in the paraelectric capacitors, and while in the ferroelectric, they are larger. So why use ferroelectric material? I mean, if they are the paraelectric material. Well, the reason is that, well, you know, it's a Peter or whatever law, with something good comes something bad, and that is that the dielectric constant is low. So you cannot make very small capacitors. In fact, today, the largest capacitor you can buy in the NPO family, something like 0.1 microfarad. Now, we want 10 microfarad, 100 microfarad, we want very large capacitances, and you cannot get it in a reasonable size with this capacitor. So whenever you can use it, that's fine. But unfortunately, in many, many applications, in most of the application, I should say, you just can't use it. Okay. So here again is the classes, COG, the class 1, X7R representative of the class 2, Z5U representative of a class C. Class 3 is also ferroelectric. It's a lower grade. That's for the poor man application. It has somewhat larger dielectric constant, so it can make even smaller, but temperature-wise, dependence, and also stability, and also voltage dependence, it's worse. So this is sort of if you go to eBay and buy ceramic capacitors, that's probably what you'll get, okay? But if you go to, a vendor, then you can look at the data sheet that you'll see that these are inferior to the other capacitors. And here are some comparison. This is the COD. This is now the DC sensitivity. This one is constant. This goes down, and this one goes more. But I should say that in some situation, we'll see it in a few slides, X7R also can go down very much, depend on many things. So it's not representative, just show especially for the paramagnetic, no question, this is a very good capacitor and very stable. So to wrap it up, this part here, we are talking about paraelectric, ferroelectric. NPO is the paraelectric 1, class 2 and 3 are the ones that I've mentioned. And I didn't mention it earlier. Let me just go back. I forgot to mention that the class 2 X7R are proper and used for switch mode converters, things of this nature, in which you don't have a large swing of amplitude. Okay? You have a ripple which is usually small. This is in switch mode converters. In resonant converters, obviously the swing is AC. It's a big swing of an amplitude, and therefore the nonlinearity of the class 2 and 3 comes into effect. We'll see it later. And therefore the COG and the power electric capacitor are better in this respect. But again, if you need large capacitance, you have to go to ferroelectric. So we have temperature dependence, and here again there are some standards available for the industry, and here are types of materials I'm not going into, and then there is the and this is for the temperature dependence. Each of these material is sort of best in the indicated temperature range, and these are the, again, it's a standard. Each one of the ranges has a designation. What is the percent change that you expect in this range, percentage in this range. So this is just now a comparison here. Again, the COG is of course constant, but you see X7R is the one that is kind of looks pretty good. Here it is, while others are less. X7U is not, and this one is very bad. This is a class 3 type material, which is changing very much. Again, it has a little higher, it could be made smaller. Okay. So if there are no questions, let me go ahead with some more basic data. What are the basic parameters of a capacitor? Now, I'm here omitting first the inductive part, self-induction. I'm just showing the ESR and capacitor, and this model assumes that the losses are due to the current flowing through this ESR, which theoretically I'll show is incorrect. The losses are not due to current through ESR. But it's nice, you can do it, and it's been now used in the industry and sort of adopted. So this is the model, and to characterize a capacitor, we're talking about the capacitance, the maximum voltage, temperature, ESR, this thing, and again, this ESR is dependent on many things. We'll talk about it. Dissipation factor, which is a little bit something of a mystery to some, so let me just say the dissipation factor is nothing but the angle due to the two elements of this impedance, and in particular it's ESR over the impedance of the capacitor. Now, impedance of a capacitor is measured at a given frequency, and as it turns out, the industry adopted 1 kilohertz. It's been done many years ago, and it is already now. So one has to be aware that this is defined for 1 kilohertz. And so the dissipation factor can be translated to 2 pi f, that this is the 1 kilohertz, the testing capacitor ESR. Or ESR can be calculated from the dissipation factor, because not always ESR is given. Many times in a capacitor, the vendors are giving the dissipation factor, and then you can just divide it by this. You have to, again, be careful that this is 1 kilohertz, not your operating point, 1 kilohertz or something like that. Then you'll get a very small number, which is unrealistic. Now, losses, of course, are represented by the dissipation of this virtual resistor, and they are the square root RMS times ESR at the operating point. There's one more thing that I like to, or two more things. One is the maximum ripple current, which is defined. This is especially related to temperature rise. That is, if you could have cooled the capacitor, the current could be higher, but there is a limit to the dissipation. And then there is a question of aging. All capacitor age, and it's interesting that the aging is in percent per decade hours. That is, every decade of hours, it's the same percentage. Typical numbers today are, I don't know, 1% in 10,000 hours, or maybe 100,000 hours. This is something like that. So, then there are some extra parameters, and this slide I'll skip because I'm going to talk about it, so let's not spend the time on this, and go into the data sheet, which is very important. So, okay, now typically we are going to have from the vendor data sheets of this nature, and they are more oriented toward switch mode power supplies. And for example, here is the buck converter. We have at the output on this is the filter capacitor. We have a ripple, and then we have a current through the capacitor, which is the AC component going here and here. So the information we have is, of course, size, and then some graphs that I'm now going into more details, okay? So the first part is the size, of course. Material, this particular one is E5R, it's a ferroelectric. Then the maximum temperature, size, tolerance for the capacitance, dissipation factor, you see this is 3%. And well, this is insulation, this is the leakage, which is usually very good, so there's no problem there. Now, the more advanced model of a capacitor will include the ESL, which is the equivalent series inductor. So this is the impedance that we have, and as the temperature the frequency changes, the impedance will go down, first of all, as 1 over omega c, because this is very small. This is still, the impedance is small, and we see just the capacitor. 1 over omega c in a log-log scale is a straight line. So this is the straight line. And then we hit the resonance between this and this, and at this point, the reactive elements are canceling each other. We are left with the ESR. So this is this point here, the ESR, beyond which we are going to see the ESL, okay? This is now beyond this point. The ESR itself is a function of frequency, as we can see it here. It's at low frequency, it is very high, and at high frequency it's becoming smaller and smaller. At this point, they are equal because the impedance drops to ESR, so they touch each other, while the ESR continues its own way later on. Now, so we have this point, and obviously the range for operation is up to here. You don't work beyond it, although this could bring you a lot of trouble. I'll mention it in a minute. Now, the capacitance change with frequency is usually not that much. So we see here up to here it's not capacitance, it's a complex impedance because they hit the resonance, and but you see it's pretty constant. Now, another information the vendors are giving is the current that is allowed. Again, I've just said that missing here is what is the pad that they are talking about. That is how much is copper below the capacitor, because this copper acts like a heatsink, and this is not specified, so one has to be careful here. Anyhow, what we see here, this is the current that RMS current, the AC, you can pass through the capacitor. This is 1 megahertz, and this is 100 kilohertz. Now, why is this? Because the ESR is 100 kilohertz is higher. So the same current will cause a higher dissipation, and you are limited by the temperature rise. This is temperature rise here. So therefore, you can pass a lower AC current than at high frequency. Maybe here is a point to say something about, well, it's not exactly capacitor, but the use of capacitors. And I found that many engineers sometimes are not aware of what's going on, and that is the following. In many designs, we put a 0.1 microfarad in parallel to 10 microfarad. I've asked many engineers, why is that? It's customary. Okay, so I'd like to explain why is that. So, because, 0.1 microfarad in parallel to 10 microfarad sounds kind of strange. I mean, you have already 10 microfarads. What will it add? Well, the point is exactly what we are talking. Okay. The resonance of a 10 microfarad capacitor will be at low frequency for two reasons. Why the capacitance is large, and the inductance will be larger due to the size. While 0.1 microfarad will be much higher, the resonant point. Now, if you put these in parallel, then at this frequency here, the 10 microfarad is doing the job. The 0.1 microfarad, which has a much higher impedance, because it's 0.1 microfarad, is like a open circuit in this case. So the 10 microfarad is doing the filtering. But if we go to this frequency, the 10 microfarad is already inductive, so it doesn't do anything. And the 0.1 microfarad now comes into effect, and it helps to attenuate the high frequency. So this is just a sidetrack here. Now to the change of capacitance with voltage. We have a plot like this in which the capacitance, this is a 470 nanofarad capacitor, is changing with the bias voltage. Again, this is a small signal capacitance. That is, there is a bias, an AC imposed. This is how it is measured. Bias, AC. The AC is between 0.1 and 1 volt. Each vendor has its own way of doing it. Many times it's 0.5, but this is how this is done. And as you can see, this particular capacitor, well, goes down very, very much. This is a 250 volt capacitor. So at 250 volt, it is very low as compared to the initial value. Now, here we're seeing the temperature change, and here are 2 points. Actually, this is without bias. This is a larger capacitance. And this is with bias. At this point, it's already biased, so the capacitance is lower. This is why this value is lower, but the change is small. So capacitance does not change very much with temperature. And here I brought you some interesting plots which are showing a couple of things. Number one, here is a comparison between a COG, that is a paraelectric capacitor, and a ferroelectric capacitor. And I'm comparing it to 0.01 microfarad capacitors, here and here. And obviously this part should be the same, but you'll see that the paraelectric or COG or MPO goes to very low 10 milliohm ESR here, while in the case of the I think it's X7R, yes, it is X7R, it goes to, well, above 100, so it's 10-fold. The ESR is much larger in the ferroelectric capacitor. And here we see the temperature effect of some capacitors. Here is the COG, which is fairly constant, and the change is in 0.1% range. Here is the X7R, and this is in 10-20% range. And also we have the Z5U, which is also fairly, especially here, it's a low. Notice that also the dissipation factor this is the ESR, is also changing with temperature. I'll show it a little bit later, the ESR. So here it is. This is from a very nice paper, little paper by Maxim, credit to them. And what we see here is amazing. We just talked about the change of capacitance with voltage, and here it is. You see 1 microfarad in this package, bigger package, this one, 1 microfarad in this package, the same material, X7R. And the voltage drop, I mean the capacitance drop as a function of the voltage is dramatically different. Okay, same material. So you see there's a big difference between the two. And of course for other sizes like 10 microfarad, you see it here. And where is it? We don't have it. 4.7 here and 4.7 here. So the difference between these, the same material, the difference is the packaging. And this is what I've said, that if the package is smaller, the electric field is larger, and they're pushing the material more into actually saturation. Okay, and this is basically the same story, so I'm not going to go over it. It's again showing the difference in the size. This is the size of the package, and same material, same capacitance. Okay, now let me talk a little bit about newcomers. There are new capacitors on the market. One of them is the Ferroelectric by TDK. Well, they came out some time ago with a big banner. We got the solution to capacitors, high current, etc. And let me just describe this and see that, you know, there are good things and there are bad things with this capacitor as well. So the interesting thing is that you can get very high current. This capacitor will tolerate very high current, like 11 amps, which is very nice. For bus bars, okay, and conceivably for resonant converter, this could be a good solution. And the ESR is acceptable, but it turns out that these capacitors are excellent or very good when operated at very high temperature. That is, you cannot get the good characteristic if you operate them at 25 degrees or 50 or 70. You have to operate them at 150 degrees. This will be the self-heating plus the ambient. Okay? So here you see it. For example, dissipation factor. At 25, here it is. This is with DC. This difference between these curves is the biasing. Okay. So let's talk about this. What is it? I barely can see it. 400 volt, the red one. 400 volt biasing. At 25, it's a lot. The dissipation factor. But if you go to 125, 150, that's very good. So in order to operate a capacitor like that, you have to make sure that it will get to the high temperature. Now, what will happen is that, obviously, at the beginning, if it's in room temperature, because the ESR is high, it'll self-heat, and it'll go to high temperature. But, I don't know, I feel kind of uneasy to work with capacitor that you have to maintain them at 150 degrees, because it has also implication about all the other components on the card. It will radiate and it will thermal conduction to the other components. So, you know, it's a very nice capacitor, but you have this is also the ESR, and the ESR as a function of voltage, and you see that the ESR is going up with the bias, and again, you get low ESR at very, very high temperature, very high temperature. Now, I did some work on the question of how to model the losses of a ceramic capacitor. And as I've said, the classical approach, conventional, is to put the ESR in series. And as it turns out, theoretically it's incorrect. And I'm sort of bringing up the name of Steinmetz, which I don't know if all are familiar with, is one of the forefathers of electrical engineering. He worked a lot with AC, developed the AC current, and he is responsible for the use of phasor analysis. That is when we write J omega and we do algebraic manipulation. This is Steinmetz's work. So he was really interesting. And one of the things he worked is about ferromagnetic material, ferromagnetics. And as you might know, there's this Steinmetz equation which describes the losses of a ferromagnetic material as a function of frequency and excitation, the B magnetic flux density. So this is very well known. But what I like to give him the credit that he also worked with dielectric material. And I'll later on show what he did and the result that I got. So if we look at the ESR dependence on frequency, we see this curve. This is up to here is the important part. Up from here is the above resonance, which is less important. And if you look at this curve, it's pretty much like a straight line. And in log-log scale, it means that it is a power of something. And it's kind of even parallel to this one, okay? So, as it turns out, you can describe this curve here as K over F, the frequency, pretty much like the impedance, which is 1 over omega c, it's 1 over frequency 2. And then you come to a threshold, which is this value. So this will be a function to describe ESR. And at the frequency and the resonance, you get this ESR sub 0, which I call. Now, if I take this expression and I plot it here, and I then put this on this, well, you can't see it. It's exactly the same. So this is the equation. This is the description of the ESR. It's going like this. And it's correct for other capacitors. Not all capacitors, I'll talk about it, but many, many, many capacitors, you have this comparison. And again, this is the curve, this is another capacitor, this is the equation, and you put one on the other, exactly the same, okay? These are one on top of the other. Now, you can, like in a ferromagnetic material, you can describe a loss either with a series element or a parallel element. In a case of a capacitor, if you put it in parallel, unlike in the case of an inductor, you can have DC. In an inductor, you don't have DC, so you don't have to worry about it. But here you have DC, and if this is a resistor, you'll have losses due to the DC too. So therefore, you have to put a additional capacitor, which is just a DC blocking capacitor, so that the losses here will be just a function of the voltage on the capacitor. Okay? So this is an alternative approach. And then by comparing the losses of this to the losses of this, I can come up with an equation that describes the losses as a function or related to this resistor, in which ESR is embedded because I'm using the function that I've just described before. That is, I'm using this ESR function in order to describe the ESR and the losses then of it. Okay? So we find then that for frequency below the resonant, that is frequencies here, the losses are a function of frequency and voltage square. This is what we get. Now, this is the more correct way of expressing the losses of a ferroelectric material, because the hysteresis curve, which is responsible for the losses, the area of the hysteresis curve is the losses. The hysteresis curve is a function of flux density, which is a function of the voltage. So the voltage is what is causing losses in a capacitor, not the current. You can describe it by, doing some manipulation. But theoretically speaking, this is the real effect. Beyond that, beyond the resonant, of course, we go back to the constant value. So in many, many capacitors, you see this relationship that I've described here, okay? In some capacitors, it's not, meaning that if you like it to describe the losses as a function of this nature, like in the ferromagnetic material, you'll have to have some other constant, alpha or beta, as we do today. Let me go back just to stress this thing. Steiner's put here fixed number. But today we know that the fixed numbers do not represent all the ferromagnetic materials. So vendors are fitting the losses to this form of equation and finding what are the constant. In this case, it'll be the same if you'd like to describe it in the same way. So and then, if you wish, you can have the same plots here. Same type of plots we have in ferromagnetic material, like P as a function of RMS with frequency as a parameter, or P as a function of voltage with frequency as a parameter. I'm sorry, I've switched this thing incorrect. This 10 megahertz should be above, and the 1 kilohertz should be below. I just copied it from here. It's incorrect. Okay. So, to sum this thing up, we can describe the losses of a capacitor as a parallel resistor to the capacitor, and this is simple function to it, VRMS and frequency. And now I'm going back to Steinmetz. Steinmetz wrote a book, Lectures on Electrical Engineering. This is written somewhere in this area, in this region. And he didn't do any experiments. He just did analytical derivation, theoretical considerations, and he said that the losses are proportional to the square of the voltage, okay? And he wrote this equation. D is epsilon times electric field, and electric field is proportional to the voltage. So this is exact, and F is to the power of 1. So this is the exact formula, equation that I have found, which is amazing. When I saw it, I almost dropped from the chair that so many years ago, this guy, out of his mind, without any experiment, he didn't know anything experiment. Magnetoelectric, ferroelectric material, he did experiment in the dielectric material, didn't do any, he just said that this should be the losses. So, I think we're going to have a short break here, and then I'm going to talk about something which is really exciting, and the ESR is a function of the bias voltage, which is very important and unknown, really unknown. So, and very important because in a switch mode converter, the capacitor is exposed to DC, and you normally, I'm not saying you, but all engineers are taking the ESR from the data sheet for 0 voltage. And it turns out that this is incorrect. Okay, so we are getting the wrong power dissipation of the capacitor if we use the ESR from the data sheet for the 0 volt biasing while we are biasing the capacitor at a higher voltage.